All right, our goal for a bit here has been to try to find the area bound by a curve in the x-axis, and we found a way to do that. Actually, somebody found a way for us, and that was about Riemann sums. And if we take the limit of a Riemann sum, then we get the exact area underneath the curve. So I know from experience, people writing down notation get very, very lazy. They leave stuff off. It's a lot to write down, a limit of a Riemann sum. If only there was a symbol that took care of all of that for us, and there is. It's called a definite integral. So our objective here is to evaluate a definite integral by writing it as a limit of a Riemann sum. We're going to see that those things are exactly the same thing. The definite integral sign, it looks like this thing. Looks like a stretched out looking S. The guy who came up with it, that was Leibniz, one of the two gentlemen responsible for the birth of calculus, the other one being Isaac Newton. So as far as it goes, Newton seems to get the most amount of credit for the discovery of calculus, except for Leibniz is the guy whose notation that we seem to use for everything. So it says here in this little picture, this illustration, October 29th, 1675, Gottfried Leibniz puts on paper for the first time the integral sign. And you can see this kind of curved scroll paper. That's what the integral sign is going to look like here. Okay, so let's recap what we talked about last time when we said the area of a plane region, an area of the region in plane. We defined it. First of all, we needed a function which was continuous and non-negative on some sort of closed interval. To find that area, we are taking the limit of, and that guy right there, of course, is our Riemann sum. Hey, what are the parts in a Riemann sum? It is a sum of products, and those products are a function value, that's the f of c sub I, multiplied times the width of some sort of subinterval there. If the width is regular, if they're all the same, then here's the formula for it, b minus a over n. They don't have to be the exact same width. However, if we're doing things by hand, they probably are going to be. And then the c sub I is supposed to be a point in each one of your subintervals that you're using to compute your height. You plug that into your function, as you see over here. What points can we use? Well, we can use the left endpoint, we can use the right endpoint, we can use the midpoint. Those are the most common ones, but you can just as easily use any point that is in between there. We have seen that when we're having to do these by hand, it's far easier to just use that right endpoint. Now, call your attention to the fact that right up here in this first sentence, your f, your function has to be continuous, and it has to be non-negative, meaning that we want our function to be up above the x-axis in order to find the area underneath the curve up above the x-axis, right? So let's see what happens when we violate at least one of those things. Here, take a look at this exercise. Example 1, find the area of the region bounded by f of x is equal to x squared minus 2x on the interval from 0 to 3. Well, as a polynomial function, we know it's continuous. So I'm thinking that part of this thing is not non-negative. In other words, part of it's below the x-axis. You know what? I'm going to stop this video here. I'm going to encourage you, since this is essentially the same thing we did in the previous lesson, see if you can come up with what would the limit of a Riemann sum give you for this particular problem. Let's see what happens when your function is not entirely above the x-axis. And then if you get stuck, hey, don't worry, I've got you covered. We'll take a look at it in the next video.